This is Chapter 4, Differential Relations for Fluid Flow, Part 6. In this video, I'll be doing another exact solution to the continuity and Navier-Stokes equations. In particular, I'm going to be looking at laminar incompressible flow in a round pipe. This is often referred to as Hagen-Poiseuille Flow. The solution is going to be done in cylindrical coordinates, so r, theta, z, rather than x, y, z. The reason, of course, is because cylindrical coordinates are more appropriate when you're dealing with a round geometry like a pipe. The main result of this calculation will be something that's called Poiseuille's law, which applies for flow in small tubes. Now, strictly speaking, of course, it's not just small tubes. It's actually low Reynolds numbers where the flow is laminar. But this tends to happen in tubes of small diameter. And it's interesting to note that Poiseuille, the 19th century physicist, French physicist, was motivated to study this kind of flow in part because of an interest in blood flow through capillaries. And then I'll end this video with an example. I'll calculate the flow in a small tube using Poiseuille's law, and we'll do a calculation of the Reynolds number to check that indeed the flow is laminar. So the problem we're considering is shown down here below. What we're considering is steady laminar flow in a circular tube. The problem definition is we're considering steady laminar incompressible viscous flow in a round pipe, and we're going to solve it in cylindrical coordinates. So our velocity vector v is a function of r, z, and theta, and so we have components vr, v theta, and vz. Now, as we did in the previous video, we're going to assume that the flow is far away from the pipe entrance, so we're away from entrance effects. We're going to assume that the boundary layers have merged and we have fully developed flow. So the flow is purely axial, and VR and V theta is 0. So we have no radial component of velocity, and we have no theta component of velocity. Theta would be swirl in the flow, so we're assuming the flow is not swirling at all. And we're going to neglect gravity. So we're going to ignore gravity effects. That's not because we have to, but it just makes the derivation simpler. If you add gravity in this problem, what you get is a hydrostatic pressure gradient in whatever direction you put gravity, but it does not affect the flow at all, so we might as well leave it out. So we'll start with the incompressible continuity equation. That's conservation of mass written in cylindrical coordinates. So we have 1 over r, di by r, r vr, 1 over r, di by theta, v theta, and di by z, vz. That's our continuity equation. Now, we just talked about the assumptions that we're well away from the pipe entrance, so there's no radial component of velocity and no swirl in this flow, v theta 0. So we can cross out these terms, and we just end up with that di by z of vz is 0. So in other words, vz is not changing in the axial direction, and so as the flow moves down the pipe, which is the z direction, the velocity profile is not changing. So the flow is fully developed, and the velocity field, and hence the axial pressure gradient, di p di z, does not change in the z direction. So we have one-dimensional flow. The only component of velocity that exists is Vz. Vr and V theta are 0. So we consider the incompressible Navier-Stokes equation in the z direction. So this is conservation of z momentum. And even in cylindrical coordinates, you should recognize the terms here, right? We have the local acceleration, the convective acceleration, we have the pressure term, and we have the viscous term. And I've excluded the gravity term because we're neglecting it in this problem. So now we can simplify this expression as we did before. Let's go through this in some detail again. It's worth repeating this, that the flow is steady, so the time derivative is 0, di vz by di time, the local accelerations are 0. VR is 0, so that term goes to 0. There's no swirl, so V theta is 0, so that term goes to 0. And the flow we just showed from the continuity equation that it's fully developed, so Vz's not changing in the z direction, so we can cross out this term. We have a pressure gradient in the z direction, and this term, di Vz by di r, that term exists. Again, di squared Vz by di theta squared, the flow is symmetrical about the center line. It's axisymmetric, so there's no variation in theta of Vz, so that term goes to 0. And the flow is fully developed. It's not changing in the z direction, so the second derivative is also going to be 0. So now our equation simplifies down. Oh, and you can also, I'm not going to do it, but you can write down the conservation of momentum in the r and theta directions. And just as we did in the previous problem, you get that di p by di r and di p by di theta are 0. All the terms cross out except for the pressure gradient term, and so we end up with the pressure is only a function of z only, which makes sense. And so we end up, when we simplify this equation, we end up with mu over r, di by di r, vr, dvz by dr. Notice these are full derivatives now because vz is only a function of r, and a full derivative for pressure because pressure is now only a function of z. Now, we discussed in the previous video at some length why this is set equal to a constant. Very quickly, because we have function of p that's a function of z and vz that's a function of r. The only way those two things could be equal is if they equal a constant. You can also think of it as that because the flow is fully developed, the shear stress at the wall is not changing, and the shear stress at the wall is what's causing the pressure gradient. And so the pressure, you can expect the pressure gradient to be constant. And of course, it's going to be a negative number because pressure decreases in the flow direction, which is the z direction here. So that's a quick recap of what was in the previous video. So I've just rewritten the simplified expression here that we have. What we're going to do now is integrate this. So I've separated variables. I brought over r dr over to this side and mu down to the bottom. So r dr and mu. And now you can perform a first integration, noting that dp dz is a constant, of course. We just made that argument. And so this becomes r dvz dr, and then we have an r here, so that's going to become r squared upon 2. That looks right to me, plus a constant. And now I've done a little simplification. I've divided through by r, and so we have dvz by dr, 1 over 2 mu, dp by dz r, and then c1 over r. Now we're going to use the boundary conditions, if you like, to determine that constant. We're going to use the fact that the flow is symmetrical about the center line. We don't expect, well, it has to be, right? The flow on the center line, we have no change of Vz in the r direction. So di Vz by di r on the center line has to equal 0. And so if we apply this, that's got to be 0. We put r equals 0. The only way, of course, r equals 0, and here is going to make this term go singular, become infinite. The only way we can have 0 equals 0 is if c1 must equal 0. So we come to the conclusion from this that c1 has to equal 0. And so if c1 equals 0, then if c1 equals 0, that term goes away, and we just end up with this remainder here. So, and I've written it dvz by dr, 1 over 2 mu dp by dz. We've got full derivatives, of course, here. So now on the next slide, I've reproduced that result just up at the top. And now we can integrate again. This time it's very simple to integrate. Of course, when you integrate this side, it's going to become Vz, and that r is going to become r squared upon 2, and we already have a 2, so it becomes a 4. That looks correct. And then we have another constant. Now this time we're going to use the boundary condition at the wall at R equals capital R, the fact that there's no slip at the wall. So we use the no slip condition at the wall to evaluate C2. So at Vz of R has to equal 0. So we put a capital R in here, of course, which is what we have here. And we set the velocity to 0, and we get that C2 equals minus 1 over 4 mu dp dz r squared. Now we can make this substitution. We can substitute this in for C2, and we get the result. That's the velocity field. That's the parabolic velocity field. If you put r equal to 0 here, you're going to get the maximum velocity, which is r squared dp dz over 4 mu, which is the result over here. That's the maximum velocity. And the negative sign, of course, is because in a real flow, dp dz has to be a negative number. Pressure drops in the direction of flow. This is the classic parabolic velocity profile that occurs for laminar fully developed flow in a round tube. It's called Hagen-Poiseuille Flow. So now I've just reproduced that velocity field up here. And we're interested often in total flow rates, so we're going to integrate this velocity to get the flow rate through the tube. Of course, it's the integral of Vz dA, so velocity times area gives you flow rate. Now our incremental area in this case is 2 pi r dr. You can't integrate just dr because you have to keep in mind that the area of that donut-shaped disk is smaller as we move into the center and larger as we move out to the radius r equals r. And we perform this integration from r equals 0 to r equals r. So I've made the substitution in here like that, and I've made the substitution for dA in for there, and that's the result. And now you can perform this integration. It's very straightforward. Integrating polynomials is not very difficult. And what we get is Q equals minus pi r to the 4th over 8 mu dp dz. And that result is called Poiseuille's law. And if you're in fully developed flow, this gradient here, dp dz, can be just replaced with some pressure drop over some distance L. So we've just replaced that with delta P, some measured pressure drop over some known distance L, since the pressure gradient is a constant. And that's Poiseuille's law. So I've reproduced the result for a pipe of length L with pressure drop delta P. We have Poiseuille's law here. And I thought I'd just make a couple of interesting comments on this. You should keep in mind that this only applies for laminar flow. So the Reynolds number has to be less than about 2300, where the Reynolds number is the density of the fluid, average velocity in the tube, diameter of the tube over dynamic viscosity. And in most real flows in sort of pipes like in your house, the flow will be turbulent. But one way to reduce the Reynolds number is to have a very small diameter. So you'll find that flow in the very fine veins and arteries in your body is laminar, just simply because the diameter is very small. And it's amazing, the flow rate is surprisingly sensitive to the tube diameter. The flow rate depends on the radius to the 4th or the diameter to the 4th, right? So it's kind of interesting, and one interesting application is a medical application. People with asthma take bronchodilators. These are drugs that expand the air passages in your lungs. And if you take one of these drugs, and you've probably seen the inhalers, if that drug causes the airway, which can be approximated as a round tube, to increase in diameter by, say, 20%, then you get that that effect raised to the fourth power, right? So 1.2 to the fourth, you'll have an increase in flow rate of a factor of 2 with the same amount of breathing effort, with the same pressure gradient. So I'll end with a numerical example. We're going to consider a liquid with a dynamic viscosity of mu equals 0.002 Newton-second per meter squared, and a fluid with density of 1,000 kilograms per cubic meter flows at a steady rate in a tube with an inside diameter of 4 millimeters. So you can see the diameter here. And a U-tube manometer with a gauge fluid with density of 2,000 kilograms per cubic meter is used to measure the pressure drop in the pipe. And the distance between the taps of the manometer is 2 meters. And the manometer deflection is 9 millimeters. So using this information, we want to calculate the flow rate in liters per hour, assuming laminar flow. And then we'll use the result of part 1. So we'll use the flow rate to calculate an average velocity and check that the flow is indeed laminar and that the result is valid. So we start this problem with Poiseuille's law. Q equals minus pi r to the fourth over 8 mu, and then our pressure gradient is just the pressure difference over a distance L, and we're shown in the problem that the distance between the pressure taps on the manometer is 2 meters. So L equals 2 meters here. And the pressure drop between the pressure taps, we determine, this is a very simple manometer problem from chapter 2, right? And you can see, because the heavy manometer fluid is drawn up on this leg, that the pressure here must be lower than the pressure here. So I'm going to write the delta P, I'm going to express it as a negative number, because we need a negative pressure gradient to drive a positive flow. And so that's minus gamma of the gauge fluid minus gamma of the fluid in the pipe times delta H. And of course, gamma equals rho G. And so we have 9.81 meters per second squared for G. The gauge fluid's 2,000. The fluid in the pipe is 1,000 kilograms per cubic meter. And then our deflection of our manometer is drawn up on the right-hand leg, 9 millimeters. So you can check the units here. We've got kilogram meter per second squared is a Newton, and we have this makes this meters squared. So the units work out. We have minus 88.29 pascals, or newtons per square meter. Now we can make the substitution here. We have the pressure difference, which is negative, and we have the length, 2 meters. So we can make the substitution minus pi. The radius of the tube is, well, the diameter is 4 millimeters, so the radius is 2 millimeters. The pressure drop is that 88.29 newtons per square meter, 8 times the dynamic viscosity, and then we have the length of the pipe, 2 meters. And you can check the units here. Newtons goes with newtons. And this meter squared is going to go with that meter squared, and that meter is going to make that a cube. It's always worth taking a second to do that, just to make sure that you didn't miss a term. And so we get some very small flow rate, 1.39 times 10 to the minus 7 cubic meters per second. But I want to express this in liters per hour. So there's 1,000 liters per cubic meter, right? 10 centimeters by 10 centimeters by 10 centimeters is a liter. And then there's 60 times 60, or 3,600 seconds in an hour. And it works out to 0.499 liters per hour, and that's the answer to part 1. Now we want to check in part 2 that indeed we have laminar flow. So we want to calculate the Reynolds number. And the Reynolds number is the density of the fluid in the pipe, average velocity, diameter of the pipe, which is 4 millimeters, over the dynamic viscosity. And then we use, of course, that Q equals V bar A, and the area is pi d squared upon 4. So I've calculated the average velocity is 4Q upon pi d squared. So 4 times, and that's our tiny flow rate, 1.39 times 10 to the minus 7 cubic meters per second. And we have pi times our diameter, which is 4 millimeters, so 0.004 meters. And you can check, right? The units again, meters squared, gets rid of that, and we have 0.0111 meters per second. Now we have the average velocity here. We can calculate the Reynolds number. The density of the fluid in the pipe is 1,000 kilograms per cubic meter. The average velocity here, 0.0111 meters per second. The diameter of our tube, 4 millimeters. And then I've converted the units here. I've used the fact that a Newton is a kilogram meter per second squared to express the dynamic viscosity in units that will show that this is dimensionless. So Reynolds number is dimensionless, so we shouldn't have any units. So kilogram goes with kilogram, and second goes with second. And you can see that we've got this meter is going to come on top, so we have meters cubed on top and meters cubed on the bottom. So all the meters go away, and sure enough, we have a dimensionless quantity, and the Reynolds number is 22.1, which is substantially less than 2300, so the flow is certainly going to be the laminar. And that completes this problem.